Fundamental Theorem of Calculus, Part 2. We're going to start by looking at the Fundamental Theorem of Calculus, Part 2. So recall that if big F prime of x is equal to little f of x, the indefinite integral of little f of x is given by the integral of little f of x dx is equal to big F prime of x plus c. So the way I like to think about this is, well, little f of x is big F prime of x dx. So when I take the integral of f prime of x, then that gets me to the original function f of x plus c because we have an indefinite integral. So the Fundamental Theorem of Calculus Part 2 says assume that f of x is continuous on the closed interval from a to b. And once again, we have that relationship that big F prime of x is equal to little f of x on the closed interval from a to b. Then, now, we're solving the definite integral. The definite integral from a to b of f of x dx is equal to the antiderivative big F of b minus big F of a. Or this is another way to write it, the antiderivative f of x from a to b. So the additional step I'll write here to kind of help make the connection is that if I have the integral from a to b of big F prime of x, since we're saying that f of x and big F prime of x are interchangeable, right? That's part of the hypothesis. So the integral from a to b of big F prime is equal to the antiderivative of big F prime evaluated at b and then minus evaluated at a. So informally, the Fundamental Theorem of Calculus Part 2 says we can evaluate a definite integral by solving for the antiderivative, big F of x, substituting in the limits of integration b and then a, and subtracting. So notice there is no constant when evaluating a definite integral because the answer is a number. That number represents the area under the curve f of x from a to b. So this Fundamental Theorem of Calculus is a tool for finding the exact area under the curve using the notion of antiderivatives. Alright, let's jump into an example. So the integral from 1 to 3 of x squared dx. Now previously, this is a definite integral. We could approximate using rectangles, or we could use the limit definition of a definite integral to find the exact area under the curve using the limit of Riemann sums. But now we have the Fundamental Theorem of Calculus, which says that I can look at the function x squared and take its antiderivative. So the antiderivative of x squared is x cubed over 3, and evaluate this on the interval from 1 to 3. So I'm going to substitute in 3 first. The upper limit of integration goes in first. So I have 3 cubed over 3 minus, I substitute in the lower limit of integration, 1 cubed over 3. So I have 27 over 3 minus 1 over 3, or 26 over 3. So the exact area under the curve is 26 over 3. We didn't need an approximation and we didn't need to use the limit of the Riemann sums definition as long as we can find the antiderivative, the general antiderivative of x squared. In this example, the integral from 0 to pi over 4 of secant squared x dx. The antiderivative of secant squared is tangent x, evaluated from 0 to pi over 4. So notice I did drop the integral sign because I've taken the antiderivative, and now I substitute in pi over 4 minus tangent of 0, and tangent of pi over 4 is 1, tangent of 0 is 0, so my final answer is 1. Here we have the integral from 1 to 4 of 3 radical x plus 2x dx. So we have to take the antiderivative of 3 radical x plus 2x, or 3x to the 1/2 plus 2x. So the antiderivative here, so I'm going to end up with 3x to the 3/2 times 2/3, and then plus 2x squared over 2 and this is all evaluated from 1 to 4. So the 3's are going to go ahead and cancel here, and I end up with 2x to the 3 halves plus x squared from 1 to 4. And I go ahead and substitute in 4 into each x, into the entire antiderivative. So 2 and then 4 to the 3 halves plus 4 squared. So all of that minus substituting in 1, 2 times 1 to the 3 halves plus 1 squared. So here we have 4 to the 3 halves, that's the square root of 4, which is 2. 2 cubed is 8. So inside of here I have 2 times 8, that's 16, plus 16, minus here I just have 2 plus 1. So I have 32 minus 3 for an answer of 29. Here I have the integral from 0 to 2 of e to the 2x dx. So the antiderivative of e to the 2x is 1/2 e to the 2x, evaluated from 0 to 2. So we substitute in 2 first, so 1/2 e to the 2 times 2 minus 1/2 e to the 2 times 0. Well, that just gives me 1/2 e to the 4th minus 1/2 e to the 0. I can factor out the 1/2 from each term, so I have 1/2 e to the 4th minus 1, because anything to the 0 power is 1 here. So here I have my final answer. Here I have the integral from 2 to 5 of dx over x, which remember is the same as the integral from 2 to 5 of 1 over x dx. So the antiderivative of 1 over x is natural log of the absolute value of x evaluated from 2 to 5. So we go ahead and substitute in 5, so we have natural log of the absolute value of 5 minus natural log of the absolute value of 2. But we can do some further simplifying here. So first, absolute value of 5, well that's just 5, and absolute value of 2 is just 2. But our properties of logs say that because I have natural log on each of these with the same base and they're being subtracted, I can turn this into 1 logarithm of a quotient, natural log of 5 over 2. Now let's look at a different type of example that involves the fundamental theorem of calculus. So let big F prime of x equal little f of x. And we know that the integral from 2 to 7 of little f of x dx is equal to 9. If the antiderivative big F of 7 equals 4, find f of 2. So notice that 2 and 7 are my limits of integration on the definite integral. So here, what we're going to go ahead and do is think about it like this. So the integral from 2 to 7 of f of x dx is equal to 9. What we know about little f of x is that it's equivalent to big F prime of x dx. So this must also be equal to 9. Now, the integral from 2 to 7 of big F prime of x dx is the antiderivative of f prime, which is f, evaluated at 7 and evaluated at 2. So the left side is big F of 7 minus big F of 2. So that must also equal 9. So now I have one of these pieces of information. Big F of 7, the antiderivative at 7, was given as 4. So I can go ahead and substitute in 4 for f of 7, so 4 minus f of 2 is equal to 9 to allow me to solve for f of 2. So over here, if I go ahead and subtract the 4, I get negative f of 2 is equal to 5. So f of 2 is equal to negative 5. So a slightly different application of the Fundamental Theorem of Calculus, Part 2. In this example, the graph of f is shown in the figure. So this is the graph of f of x. if the integral from 1 to 3 of f of x dx equals 2.3. So we'll stop right there. So the integral from 1 to 3 of f of x, this was f of x, so the area under the curve from 1 to 3 is equal to 2.3. So I'm going to highlight that region from 1 to 3, the area under the curve. All of this is equivalent to 2.3. And we're told that big F prime of x is equal to little f of x. Then we're asked to find what is big F of 3 minus big F of 0. So this is different because I have this 0 now involved, but the information I was given was from 1 to 3. So what we want to do is think about big F of 3 minus big F of 0 as its equivalent in a definite integral form. So this quantity would be equivalent to the integral from 0 to 3 of little f of x dx. That's what I'm being asked to find. So big F of 3 minus big F of 0 is the definite integral from 0 to 3 of f of x dx. So now I want all the area from 0 to 3. I only have the area from 1 to 3. But the region that's missing in terms of area is a perfect rectangle. So all I have to do is find the area of that rectangle and add it to the area under this curved part that I was told is 2.3. So in other words, what we're really doing is we're saying this is equivalent to the integral from 0 to 1 of f of x dx plus the integral from 1 to 3 of f of x dx. The integral from 0 to 1 is a base of 1 and a height of 2 for the rectangle, plus 2.3, which was given, for a total of 4.3. So again, another application of the fundamental theorem of calculus. So working backwards, recognizing that this antiderivative evaluated at 3 minus the antiderivative evaluated at 0 is equal to a definite integral with the limits of integration 0 and 3 of the function little f of x. The fundamental theorem of calculus part 1. We have to begin by defining an area function. So our area function a of x is equal to the integral from little a to x of f of t dt. And this represents the signed area from a to x. So I want us to note that a is a real number and t is what we call a dummy variable. So we don't want to keep the same value here, x, as is the input variable for our area function a of x, because this input value for x is going to become the upper limit of integration here. So we're going to be finding the area from a to different values of x under the function f. So we just really want to think about it as f and assign a w variable, a different variable here to help us understand that this is not the exact same variable that we're substituting into our area function. So this area function starts at some number a on this horizontal axis. So I'm going to go ahead and say this is my value of a. And we're interested in plugging in different values for x. So let's say we substituted in 0. So what that means is that we're going to try to find the area between a and 0, between the curve and the x-axis. So that number is going to be the output of our function. So it's going to be the area of that rectangle. And then we can try to plug in a different number. So we can try to plug in 1. So a of 1 would be the integral from a to 1 under this function that we're calling f. So all the way from a to 1 would be this complete area here, so between the curve and the x-axis. So this is a function because we can plug in different values of x into the upper limit of integration, and if a is fixed, that's going to give us outputs that represent areas under the curve of this function f. Let's continue on with that example. So given the graph of f of x, with a of x equal to the integral from -1, so we have our fixed value of a, to x of f of t dt. So notice we're told this is the graph of f of x, but I'm going to ignore that x part, just label it as f for now, and inside of the area function we're labeling it with a different dummy variable t. So find each of the following. Find a of 0. So a of 0 means we're trying to find the integral from -1 to 0 under the function f, or f of t dt. So here's -1, here's 0. So we're interested in the area between the curve and the x-axis. Now since I'm below the x-axis, my area will be negative, and my width of my rectangle is 1, and the height of my rectangle is 2 units. So I'm going to end up with -2 as the value of a of 0. If I move on to a of 2, I have the integral from -1 to 2 of f of t dt. So we're going to continue and go all the way to the x value 2 over here, and we want the total area from -1 to 2. So we're really just adding on the area of this triangle. Now the entire answer is going to have to be a negative answer because this is all below the x-axis here. So this triangle here has a base of 2 and a height of 2. So here's what we have. The total answer is negative, and we're going to have 2 plus 1/2 base times height. So the 2 was from the original rectangle, and then 1/2 base times height for the triangle. So we end up with -4 as our answer. And now we can go ahead and try a of 6. So a of 6 is the integral from -1 to 6 of f of t dt. So we already have everything from -1 to 2, so let's go ahead and figure out where we are going to stop now. 3, 4, 5, 6. So we're going to go all the way over here and find all of this area. So we already have that this whole region is -4 and this whole region is going to be positive. So I have -4 plus, now the base of this triangle is 4 units across and the height is 4 units up. So I have 1/2 base times height. So I have -4 plus 8, so I end up with a total area of +4. The next one is asking us to find a of -4. So we have the integral from -1 to -4 of f of t dt. But automatically I should notice that the limits of integration don't go from least to greatest. The bottom should be the smaller number. So if I want to switch that, then I'm going to have negative the integral from -4 to -1 of f of t dt. So I don't want to forget about the fact that I have that negative in the front. So now I'm looking for the area from -4 to -1. So that's going to be a rectangular shape from -4 to -1, and since this is below the x-axis, this is going to be a negative area. So the base of my rectangle is 3 units, 1, 2, 3, and the height is 2. So remember that I have the negative on the outside, but I'm also going to have a negative area. So the base is 3 and the height is 2. So overall, I'm going to have a +6 as my area. Now lastly, I'm asked to evaluate a of -1. So that means the integral from -1 to -1 of f of t dt, which is nice and quick since I'm going from -1 to -1, I'm not going anywhere. So I'm not collecting any area, so my answer is just 0. Accumulation function. Another name for our area function, a of x, the integral from a to x of f of t dt, is an accumulation function because we are constantly accumulating area as we substitute in different values of x. Now since it's a function, we want to find the derivative of a of x. So in this example, we're going to find a formula first for the area function defined by a of x equals the integral from 3 to x of t squared dt. And then we'll use it to find the derivative and see if we notice anything. So let's go ahead and start with a of x is equal to the integral from 3 to x of t squared dt. So to find a formula for a of x, I'm going to go ahead and apply the Fundamental Theorem of Calculus Part 2 here. I'm going to find the antiderivative for t squared, so that would be t cubed over 3, and evaluate this from 3 to x. And so I'm going to go ahead and substitute in x first and then 3 second. So I'd end up with 1/3 x cubed, and then minus, if I plug in 3 cubed over 3. So I'll go ahead and rewrite that over here. I have a of x is 1/3 x cubed minus 9. So we've actually found an explicit formula for this area function. So 1/3 x cubed minus 9. We were able to do that because we could easily find the antiderivative of this t squared function here. So now we have just a polynomial to find the derivative, a prime of x. We're going to use the power rule. So we're going to go ahead and bring the power to the front, reduce the power by 1, so we're going to get just x squared. We're just going to get x squared. So we found the derivative, and now we want to see, well, what do we notice? So if we go ahead and take a look at our original area function here, our accumulation function written as a definite integral, if we look at the integrand was t squared. And if we look at attempting to take the derivative of an integral like this, what happened was we ended up getting just x squared out as our answer. So the a of x function, its derivative was simply x squared, which is just the integrand of our accumulation function, but with x substituted in instead of the dummy variable t. So keep that in mind. We've now arrived at the Fundamental Theorem of Calculus Part 1. Let f of x be a continuous function defined on the closed interval from a to b. Then a of x equals the integral from a to x of f of t dt is an antiderivative of f of x. Or another way to think about this is a prime of x is simply equal to f of x. Or another way to think about this, if we take the derivative of this accumulation or area function, the integral from a to x of f of t dt. So the derivative of this definite integral that represents an area function, that's simply f of x. So if you notice what's happening, the upper limit of integration, the variable in our accumulation function, simply replaced the input of the f function, the dummy variable. So the x just goes right ahead and goes into the integrand into the dummy variable. And a has to, of course, be a real number. So let's go ahead and try some of these Fundamental Theorem of Calculus Part 1 problems. So in this example, find the derivative of a of x equals the integral from 4 to x of the square root of 1 plus t cubed dt, and find a prime of 2. So first find a prime of x. So I'm interested in taking the derivative of this area function, this definite integral, where I have x as the upper limit of integration and 4, a constant, as the lower limit of integration. So on this one, we wouldn't be able to find a general antiderivative for this integrand, like we did when it was just t cubed. So here we can apply the Fundamental Theorem Part 1, which simply says the derivative of this integral is replacing the t in the integrand with the variable x. So it's just the square root of 1 plus x cubed. So essentially the idea is that the derivative and the integral are inverse functions, and they basically cancel each other out. So we no longer have an integral because we took the derivative, and the derivative and integral are gone. We just have the integrand, but replacing the dummy variable with the variable x. And now a prime of 2, we have to take the derivative before we can plug in the number, so we're just going to substitute in 2. We get 1 plus 2 cubed, so the square root of 9, which is 3. For further examples, we have find the derivative with respect to x of the integral from 4 to x of sine of t squared dt. So we have this area function of x here. Take the derivative with respect to x. So applying the fundamental theorem part 1, the x simply replaces the dummy variable in the integrand. So we end up with just sine of x squared. So we would not have a dt. We never had dt's on our derivatives, right? Remember, we're taking a derivative. We never had plus c on our derivative. So our answer is simply sine x squared. On this example, we have the derivative with respect to x of the integral from x to 3 of e to the t dt. So our problem here is that we do need the variable to be in the upper limit of integration, and if we switch, then we have to go ahead and pull out a negative. So we're going to have the derivative with respect to x of negative the integral from 3 to x of e to the t dt. But remember that constants, -1, just come down with the function when I'm taking a derivative. So here, when I take the derivative of the integral from 3 to x of e to the t dt, the x replaces the dummy variable t. So I'm going to have e to the x, but with a negative in front. So I have negative e to the x. Now we have the Fundamental Theorem of Calculus part 1, but with the chain rule. So if I take the derivative with respect to x of the integral from a to a function now, g of x, instead of just x, of f of t dt, I have to apply the chain rule, where now the g of x function does replace the dummy variable inside the integrand. So I do have f of g of x, but now I have to take the derivative of the inside, apply the chain rule, which would be g prime of x. And again, a has to be a real number. So applying this, I have find the derivative with respect to x of the integral from 2 to x squared of the natural log of t dt. So here, again, the derivative with respect to x, I do have an area function here, but instead of x, I have a function of x squared. So the x squared does replace the variable t in the integrand, so I have natural log of x squared, but then I have to multiply by the derivative of the inside. So just the inside, not the derivative of the natural log of x squared, just the derivative of x squared. So that would be times 2x. So we're only taking the derivative of the upper limit of integration, whatever that function is. So this is my answer, 2x times the natural log of x squared. And let's go and take a look at a few more. So find the derivative with respect to x of the integral from -2 to cosine x of sine of t dt. So we're going to go ahead and take the upper limit of integration, the function cosine x, and plug it into the dummy variable of the integrand. So we get sine of cosine x, and then we're going to multiply by the derivative of the inside, so cosine x, the upper limit of integration. So the derivative of cosine x is negative sine x. And there's really no simplifying that we can do here. And this next one, the derivative with respect to x of the integral from x to x cubed of 4 to the t dt. So this one is different because there's no number either in the upper or lower limit of integration. So what we're going to have to do here is we're going to have to think about this problem as split up into two separate integrals. So we're going to go from x to 0 of 4 to the t dt plus the integral from 0 to x cubed of 4 to the t dt. And in all honesty, it doesn't matter what constant you use because the Fundamental Theorem of Calculus, part 1, doesn't depend at all on the constant value. Whatever that value of a is, it hasn't affected at all what the derivative of the accumulation function is going to be. So here, I just need to split it up at a particular constant. So I'll go with 0. So x to 0 plus 0 to x cubed. And then I'm going to go ahead and flip the limits of integration on this first one. So the derivative with respect to x, the integral negative the integral of 0 to x of 4 to the t dt. And then we're also going to take the derivative with respect to x of the integral from 0 to x cubed of 4 to the t dt. So here, now we have the variable in the upper limit of integration. It's just x, there's no chain rule. So the x just replaces the t, and I keep the negative. So I have negative 4 to the x, and then plus, here I do have to apply the chain rule. X cubed goes into the t, so I am going to have 4 to the x cubed times the derivative of the inside. So the derivative of x cubed, the inside, is 3x squared. So here, we'll go ahead and write our final answer as negative 4 to the x, and I'll put plus 3x squared in front, and then 4 to the x cubed. So now finally, this was called the Fundamental Theorem of Calculus, so that should indicate its importance. And here's the main idea. The FTC Part 2 said that the integral of a derivative gives the original function. So if I have the integral from a to b of f prime of x dx, so the integral of a derivative f prime, that simply gave us f, the original function, evaluated at b, minus f evaluated at a. FTC Part 1 said the derivative of an integral gives the original function. So if I take the derivative with respect to x of an integral where x, or a function of x, is in the upper limit of integration, I end up with just the original function, the integrand, f of x. So derivatives and integrals have this inverse relationship. Now let's look at some assorted problems using the Fundamental Theorem of Calculus. Here we have the integral from 0 to 2 of the quantity 2x minus 1 squared dx. So what we're going to go ahead and do is simplify the integrand by multiplying it all out. So we're going to go ahead and write the integral from 0 to 2 of 4x squared minus 4x plus 1 dx, so that I can use the power rule for antiderivatives here and find the antiderivative of the integrand. So we're going to go ahead and have 4/3 x to the third minus 2x squared plus x. And since this is a definite integral, we are going to have our limits of integration 0 and 2 here until we substitute them in. So we're going to go ahead and substitute in a 2 for each x. So we're going to have 4/3 2 cubed minus 2 times 2 squared plus 2, and then technically minus 0 being plugged into each x. But because this is a polynomial, it's just a bunch of zeros. 0 minus 0 plus 0. And then we're going to simplify this. Our answer is a number, since again this is a definite integral with numbers as limits of integration, so this represents an area. And we're going to have 4/3 times 8 minus 8 plus 2. So 16/3 minus 8 plus 2. And if we make them all have common denominators, we have 16/3 minus 24/3 plus 6/3. So we get negative 8 plus 6. So that's negative 2/3. So we get negative 2/3 as the answer to this definite integral using the Fundamental Theorem of Calculus, where we take the antiderivative of the integrand, but first we rewrote the integrand after multiplying everything out and not doing that common mistake of distributing the exponent, which we cannot do. Let's take a look at the second example here. I have the integral from -1 to 1, so another definite integral, of the quantity x cubed minus 4x squared all over 2x dx. Now again, I want to take the general antiderivative of the integrand, but I have to do some simplifying. So I have to recognize that I can split this up, so we can simplify x cubed over 2x minus 4x squared over 2x, because I need all my terms added or subtracted in order to use the power rule for integrals. And so we're going to have the integral from -1 to 1. We're going to have 1/2 x squared, so x cubed over x becomes x squared, and the 2 has to stay on the bottom, so there was a 1 on the top in front of x cubed, and then the 2 stays on the bottom, and then we have minus 2x dx. So we're simplifying. 4 divided by 2 is 2, x squared over x is just x. So now we have just these two terms subtracted, and we can apply the power rule for integrals, take the antiderivative here. So we're going to get 1/6 x cubed, right? So add a power, divide by the new power, makes this 1/6 x cubed minus x squared. So add a power, that will become x squared, divided by 2, the 2's will cancel. And then we have from -1 to 1. And then we're going to plug 1 into each x, and then subtract, plugging in -1 into each x. So we have 1/6 minus 1. So what I did there was just plug a 1 into each x. So 1/6 times 1 cubed is 1/6. If I plug in a 1 right here and square it, I get -1. So that's plugging a 1 into each x. And now we're going to subtract, plugging a -1 into each x. If I plug in a -1, -1 cubed is -1 times 1/6 gives me -1/6 minus, if I plug in -1 here and square it, it becomes +1. So we have -1. So just make sure and be careful with the negatives, take your time with it. Here we're going to get -5/6 minus, this -1/6 minus 1 is -7/6, and then the minus a negative will become a positive, so we end up with 2/6, which reduces down to 1/3. So we have two fundamental theorem of calculus problems. We find the general antiderivative, a little bit of algebra first to make it so that we can find the general antiderivative quickly, and then substitute in our upper limit of integration first, then subtract, plugging in our lower limit of integration. In this next example, we have the integral from 2 to x of cosine of 2t dt. And here we are finding a definite integral, but there's no number in the upper limit of integration. It's just the variable x. But we're still going to proceed in the same way of finding the general antiderivative of the integrand, and then plugging in x, and then plugging in 2. So the general antiderivative of cosine of 2t is going to be sine of 2t times 1/2, and that's going to be evaluated from 2 to x. And so we plug the upper limit of integration in first, just as if it was a number. So we get 1/2 sine of 2x minus 1/2 sine of 2 times 2, which is sine of 4. And so that's the answer here. It's not a number because we didn't have numbers as our limits of integration. One of them was a variable. Now I like to do this problem right before this next one here, which is the other part of the fundamental theorem of calculus, and something that students kind of tend to mix up. Sometimes students see a variable in a limit of integration and just think, oh, I just plug the variable in to the dummy variable, right? So plug the x into the t anytime I see that. But the only time I do that is if I'm taking the derivative of an integral with a variable in the limit, the upper limit of integration. This didn't have a derivative in front. So this operator, right, the integral sign says, take the antiderivative of what comes next and then plug in x and then plug in 2 and subtract them. But when the derivative operator is in front of the integral operator, that's that inverse relationship of the fundamental theorem of calculus. So on this problem, the derivative and the integral would cancel, and the x basically just pops into that t there, making the answer cosine 2x. And that's it, right? Cosine 2x. So since we're taking a derivative, there would not be a plus c, right? That doesn't make sense. There was never a plus c with derivatives, right? And so the answer is just a function. Now, just to kind of show how it does relate to the previous example here for a second, on this example, it was missing the d dx, right? It was missing the derivative, the instructions to take the derivative. But what if we put this d dx in front of our answer here? So if I have d dx of 1/2 sine of 2x minus 1/2 sine of 4. Well, what's the derivative of 1/2 sine of 2x? Well, it would be 1/2 cosine of 2x times 2. What am I using here? The chain rule, right? The derivative of sine is cosine. The derivative of the inside, 2x, is just 2. So the 1/2 and the 2 would cancel. And then 1/2 sine 4, that's a number. I don't know exactly what it is or approximately what it is, but it's a number. And so the derivative of that part is just 0. So look what I have left. Just cosine 2x, which is exactly the answer over here. So this is just another example of, how that fundamental theorem of calculus works in like a specific case. So here we could have taken the general antiderivative, plugged in x and 2, then taken the derivative. That's an option, but now we know that it works in general if I have the derivative in front of an integral with the upper limit of integration as a variable or a function of a variable. Then we can simply just say the answer is the integrand, because these two cancel out. Now the last answer here is just that extension to this part of the fundamental theorem of calculus. I have the derivative with respect to x of the integral from 2 to x squared of cosine 2t dt. Now on this one, it's not just an x, it's an x squared in the upper limit of integration. It's a function of x. So when we use the idea that it's going to cancel out and the x squared goes into the t, we're going to have to be careful. So we are going to have cosine of 2x squared. The x squared goes into the t. We have to take the derivative of x squared and multiply it on the outside. So we're going to have a 2x. So when we talk about inside for this part of the fundamental theorem of calculus, we're taking the derivative of whatever function was in the upper limit of integration. And if you think you're going to forget, do it for all of them. So even on this previous example, right, the function up here is x. What's the derivative of x? 1. So we could have put times 1 in the back, right? So you can think about it as you're always doing the chain rule. Put the function of x into the dummy variable and just always multiply by the derivative of the upper limit of integration. So here it's going to be boring, it's going to be 1, but here it was 2x. So typically we'd see the 2x in the front. 2x times cosine of 2x squared is my answer. And make sure, 2x and 2x squared do not multiply together. So this is it.